yeah, I'm going to talk a little bit about low-cost open source CPC that we're working on called the OpenCPC. So the motivation for this is as we look out there in terms of the pandemic, wildfire, snow, or air quality, it's really highlighted that we really need a clean indoor air pollution, and can really only fix what we measure. And we really are trying to focus on getting affordable, globally available, robust instrumentation to expand aerosol science outside of just this conference here. And that drives low cost to tackle affordability, that's open source, or globally available, and simple means that it is robust. So why are CPCs so expensive? And typically, when you look at a CPC, one of the most expensive components within it is the optical counting portion of it. We started with the design here, where we started with this project, and it turned out it was quite expensive to do this. So what you have is you have typically a laser diode that goes into a calibrating lens, then to a cylindrical lens to focus over a nozzle, and two nice big aspheric lenses for your forward light scatter. You have a precision nozzle. All this adds up to a lot of precision machine parts, a lot of precision assembly, fine precision adjustments, and that's cost. Just the glass, the lenses alone, at small volume are about $350. So to assemble this is on the order of about $1,000 to $2,500, which when you add that into your bill of materials cost and into your sales price, it's going to add about $3,000 to $7,500 to your CPC. So already we have failed at the low cost of the design, like the classic design here. So we need to make it cheaper. So how do we make the optics cheaper? And what we want to do is leverage what happened with the low-cost optical particle counter space that maybe you're all familiar with. So example, in 2016, MyPart was an open source OPC that basically took a focused laser beam with a 90-degree photodiode and was able to detect 23 micron particles. And the total bill of material cost of that device was around $50. And that focused laser is really important because when you go from a very large beam, like in the previous design I showed, it was a 1.5 millimeters by 40 micron beam. When you reduce that to 34 by 34 micron, very, very tight beam, you increase the intensity of that laser by 52x. That means you get a lot more signal. And that means you can have a lot less sensitive forward scatter collection. And the other important thing was a flat design, which they integrated into it both the laser housing, the apertures, beam stop, all of that is integrated to one part, and so you can significantly reduce your part count. So here's the OpenCPC optics design. So we use a SLA 3D printed housing. We use off-the-shelf lasers, a 5 milliwatt, 650 nanometer, tightly focused spot, 34 by 34 microns, at a 25 millimeter working distance. The key thing is our lensless forward scattering collection. So we actually just take, and here's an example of this, we actually just take and collect the forward light scatter right onto a photodiode, so there's no lenses at all. And we capture about 6 to 45 degrees in the polar angle. The azimuthal angle a little different because it's not a round photodiode, it has a knob angle and stuff like that. We also use an integrated beam stop. So the first reflection surface is actually the edge of the photodiode, and then it reflects into an integrated beam stop within the housing. One important thing is that, our system is that the laser relative to the photodiode is all fixed. So it's all mechanically fixed, we don't have any adjustment. How we get our adjustment is that the nozzle is actually located on the eccentric can, basically. And so we have this handle here, you turn that rotates the nozzle and brings the nozzle into the beam. So it simplified the alignment mechanism. We also, our laser is smaller than the nozzle diameter, so we're only going to count a portion of the flow coming out of the nozzle. And in this case, we actually made our nozzle out of a 0.58 millimeter Nordson dispense bit. We used for adhesive dispensation. That precision nozzle costs a whopping $1. So the total cost of this assembly, everything you're seeing here, including the electronics, including my time to build it, is $60 at 1D5. Okay, so let's do a little checkout to make sure this optics system is working. Use some 3 micron PSL atomize. And what we see here is we get a nice big signal here. There's also some that will clip. You'll hear me talking about that a lot in this talk. This is the plot up here of a plot also that clips. We only have a 1.8 millivolt or 1800 millivolt rail. So once it hits that, any signal on that can't go any further. So we can take the scattered angles that we have and the expected size range of the particles we have for the system, and we get around, we're expecting to see for 950 micron particles about 4,000 to 8,000 millivolt signal. We made a nice little simulator here, so you can put particle size versus our expected voltage. And like I said, anything over 5 microns, you can put by every factor at 1800 millivolts. What is unique is this pulse height distribution. This is not what you typically see in a pulse height distribution in a CPC. So why is that? So when we look at a traditional design, the laser beam is much wider than the nozzle. And in doing so, what happens is that all the particles traverse the laser beam, and you get this nice Gaussian pulse height distribution, which is really a function primarily of actually just varying particle size, not so much the laser intensity. When you go to our focused laser design, you get a very distinct different distribution. It has this kind of pulse height here, and then it just scales up to a 0. And the reason is that, well, the beam is obviously smaller than the nozzle, so there's going to be a lot of particles that have 0 signal because they never traverse the beam. And so here's a good example of that. The orange line is a traditional laser intensity across this, pretend this is the nozzle from 0.3, negative 0.3 to 0.5. That's a traditional laser beam intensity profile, and here is our laser beam intensity profile, this sharp curve. And you can see a particle traversing here gets no signal, whereas if you go through the traditional beam, well, then you get some signal. So this distribution is due to that mechanism. And we see that in the real world. So our simulation matches our real world pulse height distribution. So it's only going to count a fraction of the particles. And that's one of the things that we have to do, because our net nozzle is smaller than the beam. Or sorry, the laser beam is smaller than the nozzle. And the fraction of particles are counted turns out to be size dependent. And the way to think about it is that larger particles are going to give you more signal. And more signal means that you have a larger detectable area. Because the detector has a dynamic range limit. You can't measure below a noise level. We can't measure 0 volts. We always have some noise, so we can't resolve everything. And the way to think about this is if you were to look at this, pretend this is the nozzle on the left and the right, and if you have a 1 micron particle, that's the yellow one right there, your effective area that you can view is just this little window right there. Anything that goes outside of that is no longer detectable. But you go to a bigger size, more detectable. And if you go to a really big size, you're seeing much more signal out of it. So now, what you do is you have a size-dependent count fraction is part of this detector. Now we're going to say, okay, well we can model that. So we took our nozzle and our laser and this noise floor. We can create this simulation, which gives us our count fraction as a function of the diameter. And the question is, do we ever need to correct this? Like our CPC is really great, but they just generate everything between 9 and 15 micron, and we're going to be just fine. Okay, so we'll talk quickly a little bit about the CPC design. It's not too exciting. We've seen a lot of these in the past. So we're doing a typical laminar flow CPC design. It uses a working fluid of isopropyl alcohol or propanol. It has a 0.1 liter per minute sample flow rate. One thing we do a little bit unique is that we use a bypass flow rate. That reduces the transit time in the sample line. But what we also use that bypass flow is to bypass the CPC and introduce it into the optics. So the problem with isopropyl alcohol, it's going to condense at low temperature. We have supersaturated vapor, and our optics is plastic. We can't keep it. So to avoid condensation in the optics, we use this bypass flow to effectively dilute the isopropyl alcohol and reduce it below the dew point or the saturation vapor pressure. We also use tech controllers for both heating and cooling on twice that. This is a cost-saving mechanism. We already had to have a heat sink, so making it twice as long doesn't cost much more, and we can duplicate with technology. Our pump control is just basically we just use differential pressure across our optics nozzle to control flow rate. And using all this and putting it into a CFD model, we have a predicted cut point of around 50 nanometers at our operating conditions. So something we did to simplify the system is we're using a pumpless and valveless liquid handling system. So we have no valves, no pumps. What we do is we have a reservoir at the bottom that you fill. There is a PET fiber wick. For those who are not familiar with PET fiber wicks, they're inside every highlighter that you buy that's holding all the liquid in the highlighter. It works great, and it uses, we basically use capillary surface tension to wick up liquid. It's in context to a Porex wick. It's commercially available. It's a little bigger than we like to, but we just thought what was off the shelf at the time. And that wicks up any condensate that forms in the condensate section just drains back into the saturated section, and all of the reservoir here is also SOA printed. All right, so we want to make some reference measurements to this. We want to know how well does the OpenCPC compare to another commercial CPC. Does it work at all? I'll just point out that our size distribution of our test aerosol is 150 nanometer with a GSD of 2.1. Key thing is trying to keep that aerosol out of the cut point. We haven't characterized the cut point really well, mostly because we don't really well yet, because we don't have quite the equipment set yet. We'll get there. So we're going to stay out of the cut point area for this comparison. Okay, so here's the results. Wow, perfect, right? So we have OpenCPC over here. It's counting not all the particles relative to our 3225A. We're counting, roughly 7.3% of those particles. We have a nice linear fit. We could all head to the beach and have a beer, right? So not quite. So of course, it's always I love those plots, but they hide the details. So one assumption of uniform particle growth is not correct. So I assume that we generate 9 to 15 life would be great. It turns out that that is not correct. What actually happens is that as we reduce the concentration of the particles, we're seeing that the low concentration, we're actually counting a larger fraction of particles. And this is due to because the particles are growing bigger. And we see that in two places. We see that our average pulse height is growing larger at lower concentration, and also the pulse width. We do clip, but we still get information from that. Wider pulses are bigger, and we see that happen too. So particle size is changing with concentration, and that's a problem for a CPC. So larger particles equal more counts, and then we need to correct for that. So how do we do that? So we develop the correction method. So in operation, most of the pulses that we have hit that rail voltage. You can't see them, they clip. And so what we find is that you can actually, there's enough information in the pulse type distribution to correct for this. So what we do is we came up with a threshold count ratio. We basically compare the counts that are above the, basically I put some threshold value, called it above threshold. And then we compare that to the ratio of the sum of counts from the noise floor to the threshold. We call this below threshold counts. And if you use this ratio, there's enough information in this distribution to give you enough information about particle size. So if you take that model that we had generated, and using a Monte Carlo simulation where we simulated from a wide range of particle size, from 3 micron up to 50, we simulated a wide range of GSEs, of wide distribution of particles, different amplification. And if you use that Monte Carlo simulation, you compare that to the count fraction versus this ratio that we're talking about. You get this beautifully perfect linear line. It becomes indeterminate near zero, because you don't have enough information at that point. But if you use this count fraction, you can actually correct for different, basically as they grow bigger, what fraction are going to be counted. So we wanted to, this was too nice, I didn't believe it first either. So we wanted to recreate that with some empirical data. And so to do that, we used a combination, we didn't have a low ag or something like that. So we needed to generate a whole bunch of different particle sizes. And to do that, we knew that we could vary the concentration, that clearly has an input. We could change the saturator and condenser, delta T, so increasing that to make them bigger or smaller. We can change our amplification on the detector board, and we can modify our laser power. So we created this random sequence of events, or not sequence, but Monte Carlo, basically a DOE, and tested that. So there's over 100 different data points there, different count ratio. And what we found is that, yeah, it looks nice in the series. Now, of course, there's some noise there because these are real measurements on a kind of crude setup that we have for our first design, but it does fit nicely into that linear slope. If we take that new function that we just fitted, based on that data, and we apply it to our first data set, now we get a nice pretty plot. So I just took that exact linear function, applied it to the data set. Now we are going from 0, or 3 particles per cc, up to 100,000 particles per cc. We're at 96.2%. Here's the plot of the air, which I always think is more important. Plot of the air from 0 to 100,000. We're within 15% total range, or plus minus 7.5% of a TSI 32.5A. So, what did we learn? A focus slot laser design can significantly simplify optical detector design. But if you do that, you need to have some correction for particle size change, especially when you use this focus plot smaller than the nozzle concept. But you don't have to do anything too complex. It's just a simple threshold method. We did it with an ADC, the analog digital converter, but you can also just do this with another comparator. The OpenCPC is capable of achieving up to about 100,000 particles per cc within 15% relative to a TSI 3025A. So the total cost to build everything that you saw came in at $415 at quantity 5. And future work in the space is going to include looking at Kepler measurements, coincidence, long-term operation stability, maybe some alternative working fluids like EMSL. That sounds pretty interesting. That's very cool. And we'll have our full alpha release launch soon. So all the hardware you saw here, all the electronics, all the software, that is all open source. You can watch our website and we'll have an announcement when we figure out between GitHub or GitLab where this is going to launch. So here's a picture of the device right here, the actual functional device. And instead of a banana per scale, we're going to use a TSI 3025 per scale. So that's what it looks like. All right. So thank you.
Thank you. Thank you. We've got time for any good questions.
So it is great to see the linear trend. Of course, aerosols vary across multiple orders of magnitude in terms of concentration. So like log plots can hide those errors, so it's good to show it on a linear scale. But what does it look like on a log scale? Okay, as the concentration drops, so you're still quite reliable. There's some, I don't know, structure in the error at those lower concentrations as well. Are you at all concerned about that or considering it?
I think we need to improve our method of measurement. So one of the challenges with the CPC is that it only counts a fraction of the aerosol. So at low concentration, you just don't have a lot of counts. And so we have a pretty, crude lab setup that we're working with. And so we just need to improve the mixing probably between the CPCs, just get more uniformity there and longer averaging time. Those measurements will make 30-second averages. I think based on the average, we get more, or reduce the uncertainty and reduce the variability of at the low concentration. So that's where I think we'll be focusing more on that to get that resolution there. But yeah, I think that's a very good point.
Any other questions? And here at the front, just the last one.
Thanks for the great talk. A question about the light scheduling of the particles. Have you done any calculations of the scheduling, either your selectively beam or left or right hand side? And did you optimize the position of the detector, or is it just visual?
Oh, I guess I don't have the slides anymore. So as part of that model, that's exactly what that model included was as the beam moves, as far as it moves to the left or right side of the beam, that Monte Carlo simulation included that. So we assume we have a nozzle, there's uniform particles coming out, the focus beam, and what particles will pass through across the entire cross section of the beam. And that's really critical for that correction.
But did you do some ray tracing calculations or something?
No, I just use classic use scattering theory for Gaussian beams. So we
assumed an angle.
Yeah, assumed an angle from 6 to 45. We ignored the polar angle change because the photodetector is not round and it's got weird shapes, so we just kind of took the azimuthal angle, but it worked to be close enough with just the azimuthal angle on the photodetector.
Thank you.
No problem.
Thank you. Before we say a final thank you to Eric